Hello and a warm welcome from the studio here in Erlangen, and I gladly welcome you to our third tutorial in our series around busbar protection. Today we will focus on the application of a centralized SIPROTEC 7SS85 and the CT dimensioning. And it's not me giving the webinar, it's me, Michaela Mönikes, giving you an overview on the webinar, but it's my two experts here in the studio that will present the important information for you. So I'm really happy that my dear colleague Nina Hühn is here with me in the studio, and my dear colleague Rainer Gobler. Rainer and Nina, I think by now you might already know, are definitely protection experts, really experienced engineer around busbar protection. Rainer is even a member of some SIGRE working groups and around IEC definitions. And the best thing about those two is they will share their knowledge with you out there. And so let's start with a short glimpse into today's agenda. What can you expect from us today? We will start first with a short recap of the SIPROTEC 5 configurator. Nina will give that overview. Then Rainer will continue to bring you knowledge on how to configure a centralized busbar protection with DIXI 5. Nina will then continue your journey and let you experience how to test the centralized SIPROTEC 7SS85 busbar configuration with a SIPROTEC digital twin. And last but not least, we already mentioned that in the beginning, you will get to know more about the CT dimensioning. And so you see a lot of breaks in between. We want to have this a vivid session. So before each break, we will do a short question and answers round. Not only the one at the end of the session, but we will take some minutes for first question and answers after each of the 3 blocks. And to make you part of this conversation, because it's not me that will have the questions, you're out there are the almost experts here in the studio, are the experts around the SIPROTEC configurations. So please put your questions into the questions and answered field, and I will be your voice at each question and answer round and ask your question directly to the expert. And I think, Nina, by now it's time to start, right? So have fun with Nina presenting the recap of the SIPROTEC 5 configurator. Nina, the stage is yours.
Okay, thank you, Michaela, and yeah, welcome also from my side, of course. At the beginning of this tutorial, I want to give a short recap of the SIPROTEC 5 online configurator. And today we are talking about a centralized busbar protection. And for this, we prepared a small example configuration for this centralized approach. And this can be seen here on the slide. We have a double busbar with 4 feeders and 1 coupler. 2 feeders on the left side of the coupler, 2 feeders on the right side of the coupler. And the coupler has 2 CTs. Okay, so let's check what are the bullet points for the configurator. We have 4 feeders and 1 coupler, so 5 base on total, and 6 current transformers in this overall configuration. We have a double busbar, and in this case, for this, we need 2 bus zones. The disconnector image is necessary because independent of the disconnector position, a CT can be assigned to the different bus bars, and whenever this is valid, you need a disconnector image. So the significant feature I want to choose later is the 2 zones with 4 base and including the disconnector image. The functions we want to configure today is the 50BF, the breaker failure protection, 50EF, the end fall protection, and the bus coupler differential protection. And yeah, let's talk about binary inputs. Here I want to configure 8 per feeder bay. The 8 bays are for 2 for each disconnector, means 4 with these 2 disconnectors, 3 for the circuit breaker, where 2 of them are for the circuit breaker position and 1 for the circuit breaker close command. And the number 8 of the binary inputs that we need is the start signals for the circuit breaker failure protection. For the coupler bay, we only need 7 binary inputs because there we don't want to configure external, additional circuit breaker failure protection. Okay. So much about this example. Let's jump right into the online configurator. And yeah, this is the online configurator surface here. I will switch to full screen and zoom in a little bit. I hope it is now good to read and see for you. We start by selecting here the device. And it is a SIPROTEC 5 device. Okay, so here's the overview about the device types that can be selected. We are talking about busbar protection, so this is what I choose here. And I also jump over this quick description. I think we are above this point. Already know more. Okay, now this is the point where you choose the significant feature. So the first 6 significant features are the ones for the centralized busbar protection and for the IEC 61850 compliance solution. And the other 5 options here are for the 7SS85CU distributed busbar protection. But today, the first 6 ones are the interesting ones. And as I told earlier, I want to choose the option here, 2 zones, 4 bays, and including the disconnector image. So confirm the step with next. And here you have the option to choose your standard variant, which one you want to start with. And I chose in preparation that I want to start with the standard variant V2. And confirm the step again. And here on the top of this site, you always see the overview of the device like you already selected it. So you see the base module, the expansion module you choose, and how much binary inputs, binary outputs, and current transformers are available. And as we see here, current transformers are 16, or here below it's 4 times these 4. And as we saw in the example earlier, we need a setup with 6 current transformers, so this is not sufficient, and this is where I want to start right now. So I go to add and remove modules to add an additional expansion module. And here we can see it's already one IO203 selected. And here I increase this number from 1 to 2. And then we can check in the overview. Now we have 6 times 4 current inputs, and this is sufficient for our setup. Okay, but let's scroll to the top again. Now we see here we only have 15 binary inputs and 15 binary outputs at the moment. And as I mentioned earlier, we want 8 per feeder bay and 7 for the coupler bay. This means we need 39 binary inputs in total. So 15 is not yet sufficient. That means we need another expansion modules for to get more binary inputs. And for this, I choose the IO231 here. Okay, and scroll down up to the top again, and now we see we have these 39 binary inputs, which is exactly what we need. So we can go with this setup as it is shown here. Okay, I go to this next step to the plugin and communication modules. Of course, for a centralized busbar protection, in difference to the distributed one, we need no, there are no communication modules mandatory, but typically we need a module for substation communication. And for this reason, I add the Ethernet BB module here. Okay, so I confirm the step. Maybe now this is a little bit too much zoomed in. Get a little bit smaller now. Okay. So here, once again, the overview about what we already selected. As we can see also here, it is still a small display, and this is what I want to change now. Because for busbar protection, it makes always sense to go with a big display or a large display here. Because as soon as you want to display some of the single line elements, for example, it is nicer to have more space on the display. I choose this option here. And then we still have to talk about the function points. So I open the function points calculator here. Of course, the main protection functions like the busbar differential protection for, of course, or the inherent circuit breaker failure protection are already included. But we want some more functionality. And as first, I start with the function points for the necessary base. Because I hope you remember our example has 5 base, but in our significant feature, we have only 4 base included. This can also be seen here. So there's this check with that 4 base are already included, but we need 5 here, so I increase this number. Okay, then right above this bay option, there's the bus coupler differential protection. This is a function we also would like to configure or to demonstrate here in this tutorial. So I choose this another 50 function points for the bus coupler differential. And then we need the end fault protection and the circuit breaker failure protection. So here's the end fault protection. These 5 points we need for all the 5 base. So I increase this number here to 5. And the circuit breaker failure protection, here I go with the 3-pole option. And this is a functionality we want to configure only in the feeder base and not in the coupler bay. Yeah, because typically the external faults happen in the feeder bay and not in the coupler bay. So this is a number I only have to increase to 4. Okay, and let me check my notes if I missed something. No, it looks good. So these 185 points are all we need. So I apply this and scroll to the top. Here you can see the shortcode and the long code of the device we created. And of course, you can save this option as PDF. And yeah, with this shortcode now, Rainer is good to start with his configuration. So Rainer, welcome on stage.
Thank you very much, Nina.
Short switch of laptops.
So, hello once again, also from my side. As Michaela has already told, for today's tutorial, we want to demonstrate a real example from the beginning. Nina now has configured a small centralized busbar protection. I will configure exactly the substation Nina has shown. And with this configuration, I will do now with Dixie 5. Nina will afterwards demonstrate some faults and tests in the digital twin. So we really want to demonstrate here really an example step by step from the beginning. Okay. I have already opened Dixie 5. And first step, we really want to start really from the beginning. I will create a completely new project. Project new, and I would say yes, project 2023 and the date of today. That's fine as a name of our project. Needs every time a little bit. And Nina is behind me to be careful that the project, the device I will create will exactly fit to the setup of her demonstration in the digital twin. So configuring Busbar protection, especially a centralized Busbar protection, has every time 3 major steps. In the first step, I will create the single line diagram, exactly the single line diagram from the substation you want to protect. In the second step, I will create the device and all the necessary elements in the device. And in the third step, I will assign the 2 elements from the single line diagram to the elements of the device. And these are mainly the same parts independently, whether you will configure a centralized Busbar protection or a distributed Busbar protection. Maybe there are some difference to make it a little bit more efficient between the centralized and the distributed, but they are quite low. In the first step, I will start to create the single line. So I open the single line configuration. I adapt in the first step the zooming, I would say 80% should be fine. I will just delete. I go to the libraries. I open the global Dixie 5 library. I open the types and I will start with the single line elements. And here in the single line elements, we have protection templates. And I open the protection templates and we will start, as Nina has said, she wants to show us a double busbar configuration. I will start with a double busbar and line feeder template. You could see it here. So far, fine. So
But please change the assignment of the disconnectors to the busbar. So the left one to the lower busbar.
A special feature from Nina.
How I did my configuration.
I did it in this way in 10 years, but Nina,
sorry.
No problem. So, but thanks for the hint. I would already have forgotten this once again. So that's fine. Already extend a little bit the button. So we need for base, bay2, and a coupler bay in the middle, when I remember correctly.
Yes.
And bus coupler, and here we have a coupler bay. Not necessary at the moment. We have already the buttons, so we will do. Oh, this was, I clicked wrongly. Second try. Place it here. And I guess you once again want to connect the right side to the upper button.
Exactly, yes.
So it has to be consistent. Oops. And we want to have a coupler in the so-called overlapping arrangement to have a very fast clearance time. And okay, but we will have also the bus coupler differential protection, so we will demonstrate both, but here the CTs are arranged not very well for busbar protection, and so I have moved one of the CTs to the other side of the circuit breaker, and so in the first step I have to delete the connections. pick it up, place it here, connect it to the other side. That's every time a little bit tricky. So the coupler looks fine, but we need 2 feeders more. Okay. Copy this feeder. Paste it.
If we really want to do the same configuration I did, you have to change on this feeder 3 and 4 the CT to the line side. And for the first 2 bays, it is
Okay,
bus
give me a moment.
and
Let me first finish
Yes.
the line
Sure.
elements. So, bay 5. Oh. This one. And I remember I will come to your position of the feeder once again. I guess we should call this coupler.
Mhm.
The coupler. And which feeders? Right.
3 and 4 line side.
3 and 4. Okay. Oh. Let's shift a little bit. They are line side, Nina. No, both CTs are line side. Do you want to change the other ones to Busbar side?
I think I did it, yes, but I just...
Okay. Shall I change it to Busbar side? Okay. So now I was a little bit confused, sorry. Because now I mentioned it's already line side. Both of the current transformers are line side. For Busbar protection, of course, we will need, especially in the feeder, only 1 CT, but I will demonstrate it's not necessary to remove it from the overall CT. We simply will assign only 1 CT to the Busbar protection elements. So it's absolutely fine. I get the next thing. Now we want to change the color of the bus zones. Here are the bus zones for the coloring in the online monitoring in the single line, either in the web browser or in Dixie 5. To do this, I will open once again here the properties. I will select the Busbar 1. And we see here the online color, and the upper side was red. So the upper bus zone will be the online color red.
The other one green.
So like the other one, it's green, and here, oops, a little bit deeper. Now it's green. What else should be changed? The primary rated current. The primary rated current of the feeders. Yeah, you could see is the default value is 1000 amps. It's fine for all feeder bays, but the coupler bays, I think that's should be quite near to reality. So typically in couplers between bus zones, current could be much higher. So typically there are a higher rated CT in the coupler, and we have decided here for 2000 amps. So I will select CT or CT2 in the coupler, and I will change the rated primary current to 2000 amps. And I will select the second CT, and it's also 2000 amps. Save. Okay, Nina, I am
Thank you.
ready with the single line diagram, or I forgot something? Okay.
Looks good.
So first step, I have finished now the single line diagram of the substation to be protected by our Busbar protection device. Second step will to create the device and all necessary elements in the device. Before you need the device drivers, the Dixie device drivers, the DDDs. I will just show you which DDDs I have imported. We are selecting tools and go to manage device drivers. And so you see that I have imported device drivers of the communication protocols. More necessary in the next tutorial when we are talking about the distributed busbar protection, but also typically necessary in a centralized busbar protection, because nowadays really every device, especially a busbar protection device, has a connection to a substation communication. So here I have several merging units we will need in our last tutorial. And for busbar protection, we have the 7SS85. We have from version 8.84 until version 9.40. 9.40 is the newest one. And I will create for our demonstration, of course, the newest firmware version, the 9.40. And what again is very important to see really is that we have one device which is able to make a centralized busbar protection, a distributed busbar protection, and it's only one firmware, it's one code, it's one device where you can figure really all different types of busbar protection. Okay, that should be. Let us create an centralized busbar protection with the product code Nina have created. At device. That's the P1E 118070. Let's verify. There are, for busbar protection, there are not so much application templates because simply the variety is so large it makes no sense. So we have really only a basic template where we have one bus zone. We will select them. And for the communication protocols using the firmware version 9.40, there are also no options. So you must use the 9.40. And I say, okay. And now typically we have to overbridge some time when Dixie 5 is creating the device. So importing CFC, some CFC functions. Okay, the device is ready. Let's have a look to the device view. I select the device, the 7SS85, and we can check whether the product code really created the device Nina has configured. It has a large display, only 16 LEDs, and 3 extension modules, and 2 IO203 and 1 IO231. So that's fine. Okay, before we will create the elements, we will, in the first step, create the measurement points. We go to we open the device. We open the device. We go to measurement points routing. And since 2 years, we have the very nice feature that it's possible to create in one step not only one additional measurement point. We can already create in our example up to 6 measurement points, and they will be automatically routed to the available CDs in the 7SS85. So we have, for busbar protection, only 3 phase measurement points are allowed. And the count, 4 feeders and 2 CDs in the coupler, we need 6 measuring points.
And then it makes sense to rename them, that it is to keep a better overview about the measuring points and the connections between the base and the measuring points.
Especially when you will see later when we make the assignment between the elements of the device and the single line element, and it's very helpful to be sure which measurement point should be assigned later to which bay. And therefore, as Nina proposed, we will give the naming of the measurement point according to the bay. We will assign them later. That's bay 01. Bay 02. Oops. Bay 03. I see no problems. Do you have problems with my voice? Yes, okay. Sorry. Excuse me. We have a little bit problems with my sound, as it seems. Okay. Okay. I will continue. A4 and the two measurement points for the coupler. Let's couple the first one for the coupler and the second one for the coupler. Okay. And now we will create the additional elements in the device. And therefore, there are different ways how to do this. You can drag and drop them from the library to the settings or into the routing matrix. As for the Busbar protection, we have to work anyway a lot with the single line editor. I will do the same by drag and drop them to the element to the device in the single line editor. So I will close. Normally, we should see here this device, the 7S85, and the first step you see we have at the moment only one bus zone, but we have a double bus bar, so we need an additional bus zone to assign them later. So we are here in the global DXY5 library, types Busbar protection, 7SS85 Busbar protection, function group Busbar. Busbar protection, it's a little bit exhausting, I know.
Good hidden.
But sets according to the structure in SIPROTEC 5 and in DXY5. And here we have the bus zone. And we will drag and drop them to the Busbar protection. And now we have two bus zones. And we need a bay. So we will drag and drop a bay. That's a bay 1. So let's finish the first bay first. Let's start with according to routing, we started with the circuit breaker. So let's create also the circuit breaker first to have the same order. Bay. Okay, I have to open the bay and the function group. Sorry, a little bit 3-ball. I guess you have chosen a circuit breaker 3-ball.
Yes, yes.
That's enough. So we have a circuit breaker, and should we create? Oh, let's already create the additional function in the circuit breaker. Makes it a little bit more quick here. We need
endpoint protection and circuit breaker failure protection.
So let's start with the circuit breaker failure protection. It's here. The advanced circuit breaker failure protection have to be put on the circuit breaker, and the end-fault protection with the EF we have also to put here. Anything else? No? Yep. So now next step will be the disconnectors or the current transformer. Doesn't matter. No. Oh, let's create this disconnectors. Function group circuit breaker. You have function group disconnector. And the disconnector 1. And the second disconnector.
And it is really a nice feature that we only have to do it once and then copy the bay. That saves a little bit of work.
Also, quite new node. In the meantime, I guess implemented since 1 year, but me as a PLM for Busbar Protection had to wait for this feature some years. So some features need a little bit more time, but now it's available. Very fine. Okay, and I guess we still need a current transformer. Where is the current transformer? Here's a function group current transformer, and I need a current transformer. Okay, as Nina has already said, 2 years ago, we would have to create all these elements here once again for all the base, but now it will be possible to copy the bay, and therefore before we will copy the bay, it's a good idea to save time to complete the first bay as kind of a typical as much as possible before copying, because it saves a lot of time, a lot of money in this case. Okay, now what we want to do, we have to go, let's start with the settings. Let's go to the settings, bay 1, the circuit breaker, and here's the circuit breaker failure protection. Okay, this will be too later. What is important, the start via binary input we will do, because it's used as an external circuit breaker failure protection, and I guess it's one, or
I choose the one channel.
One channel. Okay.
And a retrip T1.
And retrip T1. Retrip after T1, it's no. So we have here parallel stat, I guess. Parallel stat. And the thresholds, the delay T1 is 50 milliseconds, the delay T2 is 130 milliseconds, and the threshold, where's the threshold? The threshold says current. Okay, we haven't assigned the current transformer. Okay, this has to be done. We will have a look afterwards when we have done the assignment. Maybe a little bit problem to make it too fast here at the very beginning. Okay, maybe not to disturb you. We can't see the threshold at the moment because up to now we haven't assigned the current transformer to the circuit breaker, and we will do this later, and then we will see also the default of the threshold. Okay, what's next? Routing and the unbalancing mode, or is it? Okay, we will demonstrate the circuit breaker failure protection in the unbalancing mode, but that's already the default value. Okay, I guess that's about the settings. Nina, we have forgotten the bus coupler differential. On the bus coupler differential protection is at the coupler. Okay, we will do it later. Okay, it's not so easy not to forget something, but I would say now we go to the routing. So information routing. Let's go to the bay, and we will start with a disconnector, the circuit breaker, and we will start with the position.
And open, high, closed, high was
open, high, closed, high. Then
the close command for the N4 protection.
Protection is here. The close command. That's this one. High active. and the start of the circuit breaker failure protection. That's the fourth one. That's the start. High active. So we are finished with the circuit breaker for the moment. And let's go to the disconnector position. Next free one is a 2.1.
Also open high, closed high, yes.
Closed high. And the disconnector of the status 2. Oops, it's open high. Closed high. So, and of course, we set the sources, the binary inputs, and we need to route at least the drip command of the circuit breaker. And to do this, I will collapse the sources. And here we have the binary inputs. Let's go once again to the circuit breaker. And here we have the drip open command. And we will use two unlatched, two binary outputs. So, what do you think, Nina? I am ready now to copy?
I would say so, yes.
That's okay. Let's try. Maybe we have something forgotten, so we will do it later. Okay. Oh, let's close. Sometimes it's a good idea to close all. Okay, we will start the copying here. We have here the bay one. Right mouse click, say copy, click to the settings and say paste. And now I will be asked, do you want to route sequentially from the next available slot of binary values, means binary inputs, binary outputs, and LEDs while copying? If you select no, the routing will not be copied. Maybe a sense if you have anyway a different philosophy of routing your binary inputs and binary outputs, and then you could say no. If it's fine for you to make it sequentially, you would say yes. So for us in our demo, it's fine. So we would say yes. So we have already bay 2. Let's proceed. Copy. Paste. Once again, I will say yes. And last feeder bay, copy, setting, paste. Once again, yes. And last one for the coupler, it will not fit exactly, but we will try it and say copy. And we will say once again settings, paste. And now maybe you may be confused as we have not been asked whether the routing of the binary inputs and binary outputs should be copied. The reason is that now there are not enough binary inputs and outputs available anymore. And if they are not enough, I decided the philosophy not to copy it partly, because then you have to see anyway which should be copied and not. So I decided as BLM, okay, if there are not enough binary inputs and outputs, don't copy any of the routings. And this has been done. Let's have a look. So opening the, maybe first, before I open the information routing, it's a good idea also to rename bay 1, bay 3. It's fine so far. We will later synchronize it anyway. But here, not to be confused, let us rename it to coupler. And typically, you don't need an circuit breaker failure protection, which should be start external. Of course, we need the inherent circuit breaker failure protection, the circuit breaker failure protection, which will be started by a trip of a bus on anyway, but you don't need an external started circuit breaker mostly. Sometimes there are special configuration where we will also have an external start. But let's do here this demonstration, the most common things. And I will delete the external circuit breaker failure protection.
And then we need a second CT in this coupler.
Ah, thanks. I would have forgotten this. Okay, let's go here, the current transformer, and here it's collapsed. We have one current transformer up to now, and we need the second current transformer, and we place it to the coupler. So now we have two current transformer. Okay, and now maybe it's a good idea to create the bus coupler differential protection. Where function the extensions? Coupler zone. Okay, here's a coupler zone for the bus coupler differential protection, and I will place it to the coupler bay. Maybe, yeah, okay, as we are already in the settings, maybe let us change the setting of the coupler zone. We have the threshold for the one phase. Just for remember, if the restraint current is above this threshold for one pole fault, it will be changed automatically into the overlapping mode, where the two zones will be cleared very quickly. And the threshold for the one phase, I guess it was 5 amps. And the threshold for the multi-phase, that means the threshold of the restraint current when the bus coupler differential protection will be switched automatically to the overlapping mode. And this was, I guess, 1.
Exactly.
Okay. That's 1. And now we have to assign the routing for the coupler. As the routings of the coupler have not been copied, I open once again, and maybe let's have a look. Now here you see when all bays are really collapsed, how the sequentially routing have been done by Dixie5 during the copying. But now here it stops, and the coupler has no routing. And maybe let's, we had for each bay, we had 1, 2, 3, 4, 5, 6, 7, 8 binary inputs. But we have still 1, 2, 3, 4, 5, 6, 7 binary inputs have been available still anymore, and that's the reason this one missing binary input was the reason why Dixie5 has decided not to copy any routing at all. But of course we need, but in reality it's sufficient because we don't need the external circuit breaker failure protection. So we have to do the routing before we start once again with the circuit breaker. And the circuit breaker failure, the circuit breaker position. Where do I need where to start from? Okay, that's position. Okay, the 5.18 is the next one free. So I will start open high, close high. Circuit breaker and the
close command from the endpoint protection.
Exactly, the close command. The 5.20 high active, and we will continue with the disconnectors. Disconnector position and open high, closed high. Disconnected 2 and position open high, close high. So Nina really exactly has tailored the device what we need. There's really no binary input free anymore.
Luckily, I counted right.
Okay, and of course, binary output. We should also the coupler, of course, should open. So we go to the circuit breaker, and here we have the trip open command. We once again collapse. So, and now we need which, sorry, how many binary inputs? Yeah, okay, here we can see. So let's continue at 4.1. Breaker, oops. Trip open command 4.1. Let's again. Yeah. Okay.
And you can go to the single line and do the connections.
Anything?
Right? No,
Maybe.
no, I don't think so.
Okay, we will see. Okay, to finalize, now we have finalized 2 of the 3 steps. We have finalized in the first step to create the single line diagram, and now we have finalized to create the device with all elements in the device, including the routing with the binary inputs and binary outputs. So there's still one major step left, and that is to assign the elements of the device with elements of the single line, and therefore I am open the single line configuration. Here I have the device, and I have already created an additional busbar, and in the first step I will assign the bus zones of the busbar with a single line busbars. That's fine. So the bus zones is already assigned. And to assign the elements of the bay to the single line bay elements, it's a very good idea to use this drag and drop availability possibility of the base. So you can here select the base, and we can make it in a 2-step approach and drag them here to the single line element. Bay 2. The coupler will be placed under the coupler. Bay 3 under bay 3. And the bay 4 here. Over here. 2-stage approach. Make it so. So. Okay. Now I have placed all the bays below the bay in the single line editor. We open the bay. I guess we don't need this at the moment. Let's start with the circuit breaker. We have to do this very carefully now, you remember? Okay, let's start with the current information of the circuit breaker, and we will assign every time the first current transformer to the current transformer inside the device. And now that's the reason it's a very good idea now to give a clear, meaningful name to your measuring points, and set the measuring point for bay 1. And we will assign the circuit breaker collapse the circuit breakers. We will assign the disconnector 1. We will assign the disconnector 2. And we will assign the current transformer. Once again, bay 1. Okay. And now we have to do this for all 4 other bays. That's maybe a little bit exhausting. So if you need urgently a coffee, maybe it's a good time. But I have to do, and I have to be concentrated now to assign also the remaining bays to the elements. So once again, measuring point bay 2. Circuit breaker, disconnector status 1, disconnector status 2, collapse, it's a current transformer, that's a bay 2, wave. Coupler, circuit breaker, doesn't matter which of the current transformer you will assign to the circuit breaker. You can use one of the 2. So it's a coupler 1. And the circuit breaker is here. And the disconnector 1, disconnector 2, current transformer 1, and the current transformer 2. Of course, here now definitely the other one has to be selected. Coupler 2. Okay, looks fine. Same for the bay 3. Circuit breaker. Now it will be bay 3. This time it's working. Current transformer. Disconnector 1. Disconnector 2. And current transformer. Current measuring point for bay 3.
Okay, almost finished.
So, circuit breaker, last bay, bay 4, circuit breaker, disconnector 1, current transformer. So, bay 4. Okay.
Well done.
Hopefully. To check whether it is really well done or whether I did maybe some mistakes, you have to make a first plausibility check. And if you go to the so-called filter view, here you have the filter view. And if you go here now to the 7SS85, the algorithm within Dixie5 to really interpret the topology of the substation the device has to protect later is running. And if something is implausible, when I forgot something to assign, or when I assigned a measuring point of one bay to several bays or anything else, it will be refused, and you will get an error message or anything else to check your configuration once again. And if it's fine, you will see exactly the substation the device will protect. And you will see only these elements in the single line element which are assigned to the 7SS85 and which are valid for the protection. So let's cross the fingers. It's working. This time it's fine. And you see now what is very interesting. You see in this so-called protection view now really only these elements you have assigned to the device. You don't see these line disconnectors. You don't see anymore the second current transformer because you haven't assigned it. And this is also a very good check whether your configuration is right. Maybe you forgot to assign one disconnector, then it's a valid configuration. For example, if you forgot to assign QB2, then it's this feeder is assigned or can only be assigned to Busbar 2. It's also possible, but you by yourself have to check whether this is reality or is only the result of a fault by yourself. And maybe Nina, now we have to check. We have also base. We have the coupler. We have the coupler with two CDs. We don't see the voltage transformers. We are not interested in voltage transformers for Busbar differential protection. So it looks quite fine. And what else? You see here also measuring points, the measuring points of the bay currents and the measuring points of the check zone, of the bus zone, and about the coupler zone. And it's a very good idea now in this filtered view of the single line editor to arrange this measurement boxes, because as you arrange it here now and will save in the same order, you will see the measuring boxes later when you open the online monitoring in Dixie 5 or open the online monitoring in the web browser. So I will do this for Nina, that he will have a good prepared online monitoring for the demonstration in the digital twin later. So coupler PE1 is the left one, the coupler PE1 is the right one. Oh, that's wrong. That's bay 4. Why is it called bay 5? Did I make any?
It's bay 4 and 5, the right ones. But I think
yes, here I have
not
bay
that.
4 and okay. I have to rename this to bay 3 and bay 4. Okay.
I think we can accept that.
Yeah, thanks. But I was a little bit confused for a little moment. So now where's the bay? Oops, where's not the bay 5? 5. No, that's bay 4. I missed bay 5. Here's bay 5. Maybe now time for a little break. Okay. Yet. That's the arrangement of the measurement boxes and the very valuable filtered view to make a check whether your configuration is right. Let me have a look what I still want to. Okay, I want to synchronize. I will close. If you see here, for example, here's the disconnector names. That's called bay 0. You want, I guess, in your project, you want to name them to bay 01 and bay 02.
Yes, but
yeah, I think we have this done. Bay 0. It should be exactly project. Bay 0. A05. And if you select the device and you go here to the synchronize button, then the elements and the names and including the primary rated current of the CDs will be passed from the single line engineering to the elements of the device. It's only a single way top down. It says no logic as to make it the different order from the device to the single line. It's only really to forward the names, the settings from the single line to the device. I will push synchronize. And since the transformer ratio has been changed, the affected parameters may be adapted to the changed ratio. That's the reason why I have changed the primary rated current of the CD in the coupler from 1000 amps to 2000 amps. And as we haven't adapted any settings at all, I can simply say here, yes. Okay, and now also this red coupler is going. And we can see here that the name of the bus zones have been are equal to the name of the bus zones in the bus bar, and also here the names of the disconnectors of the circuit breakers, they are equal to the names in the device. So save the settings, maybe to have a look whether also this primary rated current has been changed correctly. We have a look to the 7SS85 settings power system. Let's go to the measurement point 1. Here we see the rated primary current is 1000 amp. And for the coupler, it has been changed by the synchronizing with 2000 amps. Now what is missing? I guess one setting.
Yes, we wanted to adapt the setting for the bus coupler differential.
For the bus coupler differential protection. Bus coupler differential protection, we have already changed the minimum differential threshold, yes. So we are in the most important settings. You remember this minimum differential current threshold should be higher than the highest load current of all feeders. It should, of course, be lower than the minimum short circuit current. And for our demonstration, we have decided for a minimum differential current of 1200 amps. The rated object current is 1000 amps. So the threshold of the differential current should be 1.2. And typically the same for the bus zone. 1.2. And maybe as we try to show the thresholds of the circuit breaker failure protection before we assigned any CDs, maybe we have also looked to the settings of the circuit breaker failure protection. Let's go to Bay 1, circuit breaker. Now we can see that there's a threshold. The threshold for the phase current is 0.5, means the threshold is 500 amps, and the sensitive is 250 milliamps. Okay. Nina, do you have fun with this project now to demonstrate digital twin?
Yeah, maybe one more point. To close the circle, show our customers how to export a SIM file.
Okay, good idea.
Which I need anyway.
And that's where to go project.
On project on the device. In the project tree, right click on the device.
Okay. Sorry. Okay, project. Then export. And then, when I remember correctly, somewhere at the end, simulation related data file, C user data. Yes, I would say let's do it to the project. Oops. system, Dixie 5 projects. And that should be the project of today. And I will locate the SIM file here.
And this is the file we upload to the digital twin.
Oh, that's great. Due to inconsistency in the file.
Okay, this was a bad idea.
But we have here the SIM. Oh, let's check. Couple overlapping. Advanced when using the bus coupler differential protection, CTs must not be overlapping.
This is
That's a good idea. Let's go to the coupler bay. I guess it is the setting general. Yes, okay. And here it's marked red. That's by default in the overlapping mode, but we have decided to show the bus coupler differential protection. And when we are using bus coupler differential protection, there's no overlapping because then it makes no sense. So we will change it to no. We will change it to no.
I think you don't just have to do the inconsistency check again and everything will be fine.
I hope so.
I'm quite optimistic. Yes.
Okay, that's live. Okay, let's go once again. I have selected the device. I say project. I say export. I once again. And I nevertheless. Let's select. Okay, it's already still the project directory. Save. Export. Okay, now it's exporting. It takes some time, and it will also take some time by Nina to import in the digital twin. And I guess it's a good idea to use this as a small break.
Yes,
No, not
a bit of a break, but I think we will start with a short questions and answers round first. So you can stay there. I try to find some space for my PC here. That was definitely a deep dive into Busbar protection right now. And we already have some questions. Let's see how much time we will take for it, because we want to continue the tutorial and start with a question that came in first. And yeah, I think you will see it soon a bit bigger right here. The first one came in from TA, and it was just complete description of Busbar protection and testing procedure for Busbar protection relay. This is not a question, but I tried to take it. This is exactly what we are going to do today. Configure and test. So I hope that the webinar will answer your question. If not, please hand it again.
And maybe once again, the hint, this demonstration will be recorded.
Yes.
And of course, there's also explained in the device manual how to configure a centralized Busbar protection, how to configure distributed, and there are also commissioning hints, how to proceed for commissioning. Okay, there's not described how to work with the digital twin.
Okay, not yet.
Not yet.
All right, let's continue with the questions. Is the 7SS85 scheme performance on breaker and a half substations better than classical high impedance schemes? And how? And what CT specification or what CT accuracy class is recommended for such applications?
Yes, I would definitely say, of course, it's better than high impedance Busbar protection, whereas for a breaker and a half scheme, maybe I would say a high impedance Busbar protection may also be applicable, as it is from Busbar protection side, there are only 2 single buses. And single buses can be also protected with high impedance. The disadvantages of high impedance busbar protection is more, and especially in complicated busbar protection configurations like double busbar, triple busbar with transfer bus. Here, high impedance is nearly impossible. And CT dimensioning will come at the end. It will become for high impedance. The recommendation is there are the PX classes, whereas for low impedance busbar protection, there are several CTs possible. I personally would recommend the 5PR, but will come at the end of the day.
So we will get more answers on that question. And then a question we even might answer a bit later because it's talking about testing, but let's take it like this. WAEV wants to know, how does the external fault detection and CT saturation algorithm work? And how can you test this algorithm?
I would say for algorithms, I would recommend our second tutorial to watch the recording. But I want to demonstrate later with the digital twin an external fault with the circuit breaker failure protection, where I start the circuit breaker failure protection with a binary input.
Perfect. Now the next one will be a bit tricky because the question is placed in French. And est-ce que je peux installer de TC de classes différentes, und so weiter? And if I got it correctly with my poor small remembrance of my French I had in school, so not technical stuff, can I use different CT classes or CTs from different vendors? That is hopefully the correct translation of the question. And you will take that one also in the written.
I guess this answer will really explicitly answer in my last tutorial.
Okay, so in the CT dimensioning,
yes.
So we will talk more about that.
I
So
guess it will be answered
tuned.
in the very first slide, so maybe we can postpone this.
Oh no, so that's our cliffhanger for the next webinar, right? Stay tuned, how to configure from different vendors and different classes. And the next one will be on April the 4th. So just mark your calendars. Next one, the selection guide for BIVOs for busbar differential. Is this a question? Is there a selection guide? Or maybe, or that's a tricky one from MB. It's just sure half a question. Let's see.
Now maybe once again, this should have been explained in our first tutorial, how to count the number of binary inputs and binary outputs.
Something in
maybe
there.
Some selection guide. So also maybe you are registered now for this tutorial, and that means you have also access to the first tutorial. And here we really explained in detail how the number of binary inputs, binary outputs have to be counted.
Perfect. So once again, please refer to the first tutorial for the selection of BIs and BOs. And then question from SR. Does it matter if you connect circuit breaker 1 to busbar 1 or to busbar 2? I think it was the one between the busbars, right? Something in between your presentation, rather in the beginning.
Of course, both solutions are possible. It is just I choose this assignment, and because we want consistent projects, I told Rainer that he should do it the same way.
Yeah, but in reality, away from our demonstration here, you give right. But in reality, it should be the same like in your real primary substation.
Yes, I think this is.
It should be simply the name of the disconnector, whether it will be assigned to busbar 1 or busbar 2 should be in parallel to your primary substation. I think that's the answer. And here it's just for demonstration to be consistent with the demo project of Nina.
Yeah, just need to be able to find it and identify it correctly in your network. And MZ wants to know, where is the CT in the SLD? So where can you find this CT in the single line diagram?
Should I once again show?
Do we still have the possibility to show it online? I think so, yes. It's there. Yeah, that's rather small to show as much information as possible, but you can zoom in.
This is a CD I have assigned. This CD may be in reality also available, but not necessarily for the Busbar protection, and therefore we don't have assigned. Maybe this CD is for distance protection or anything else, but these are the CDs and the single line element. And here in the coupler, here we have the two CDs in the coupler, and here we have the CD. So these are the elements of the current transformer in the single line.
Thank you. So I hope that answered the question. And then AMB wants to know, please clarify with one CT method in the bus coupler, is it possible to achieve BC unfold when the BC is in close condition? Or is BC a CB?
Bus coupler?
Bus coupler, okay.
Please clarify with, okay. They want somehow to make a coupler with only one CD, and they want to have bus coupler with N-fold protection. And yes, that's possible. And once again, I am sorry, this has been explained in detail in our second Busbar tutorial by Nina in the section N-fold protection. So here I give it's, I can answer, it's possible. How it will work, maybe a little bit too much time here, and you can repeat it watching the video of our second tutorial.
Fine. And there in the section with the N-fold protection, yes. Right?
I guess it was quite at the end of the second tutorial.
Me too. Yeah, I think so. So just access the second tutorial and move there to this part about N-fold protection. And now we have a question a bit longer, and let's see if that works out for you. So can you, MV wants to know, can you explain the interaction between the busbar protection, inherent BF and external BF, specifically for the unbalancing mode of 50 BF? And if we choose unbalancing for operation mode BFP, does this apply to both internal and external 50 BF? Does blocking the busbar protection influence the BFP?
Breaker failure protection.
Thanks, in this case, as the algorithm for breaker failure protection uses the logic from the busbar protection. So that's the first, second, and third question. Do the current thresholds from internal and external breaker failure protection have any relevance in this case? So the current threshold trip release equals 0. And I'm really glad that you can also read this question and that my experts can read the question. And let's see if we get any answer.
Yeah, but I think it is a little bit too less time to answer this here correctly. And I once again have to recommend our second tutorial.
Once again!
Where we talked about breaker failure protection. And how
yes, this time I explained it in the second tutorial. And it's I guess that was really a half an hour explanation, exactly what has been asked here.
So MV, just please access the tutorial number 2. And I think the same applies for your next question. It's also coming from MV around the circuit breaker and the end fault, if I see that question correctly. So I think we will give the answer in a written format to reference to the tutorial there. And let's see if we take the next one coming from SI. If we use the decentralized system with IEC 61850 compliant, is it possible to have CBF, so circuit breaker failure, in central unit? What will be the disadvantages of the same?
It is possible, and there are no disadvantages, right?
That's even better.
Or at least it costs more function points.
No, the
No.
price is not so.
Okay.
The disadvantage is a little bit that if you have circuit breaker failure protection in the center unit, the limit of the maximum base is not 24, it's 20 only, because then we get, if you have 24 base with each circuit breaker failure protection and the circuit breaker in the center unit, we will have memory problems. So the disadvantage is only the maximum number of measuring points will be 20 instead of 24. On the other side, maybe a little bit of more complicated goose engineering is necessary, but it's possible in principle and it will work.
Okay, thanks. And I think as I has more questions, next one is it possible to eliminate the switches in the centralized system? Or system without switches?
I guess they mean the Ethernet switches, yes. And it's possible since version 9.20 when we can use as communication topology the HSR.
And we will talk about communication topologies in our last tutorial.
Perfect. That's what I like about the series of webinars. You bring in wonderful questions, and we see here, oh yes, we plan to answer that. So just stay tuned for the next webinar. And I think I take first the third one from SI, wanting to know, is it possible to connect with you in case of any discussion about BBP? So directly, how to connect with you? Are they allowed to contact you via LinkedIn, for example?
Yes, it's possible, but I would LinkedIn. There are too many messages, to be honest.
Yes.
So I guess you have my email address, and the best would be to contact me if they are really detailed technical questions. I would prefer to contact me by email.
Okay, perfect. Thanks for that. And then,
I guess same for you.
Same for Nina. Thank you. And next question coming in from BQ, or came in from BQ. How many bay units can be accommodated in one central unit?
Up to 20 current inputs.
That was easy.
But maybe bay units, I guess I mean bay in one. I'm not 100% sure, because they ask central unit and bay units.
If they mean
and
centralized,
you have answered base in centralized busbar protection. And I guess they mean how many maximum number of bay units to the distributed busbar protection. I'm not 100% sure, but bay units and central unit, and not base and centralized busbar protection. And okay, bay units in our distributed decentralized busbar protection, the maximum is 48 now.
Okay, that's even more than the mentioned 20.
Yeah, okay.
In a distributed setup. Yes.
Okay,
distributed
so
setup.
Depending on the setup, we
Yes.
really
Yeah.
need to be sure on that and really specify and clarify that, right? That's the question, the problem sometimes with this question. You know exactly what you want to know, and it's sometimes tricky to get it in a written question. So if you feel that was not
Nina has
question,
answered, because today we have the topic centralized busbar protection, and Nina has answered what are the limits for centralized busbar protection. Absolutely correct. But according to the wording in these questions, I guess it's more related to the distributed busbar protection.
Yeah. Okay, I hope we got it. If not, get in contact. And I think we take one last question. Is there any free simulator existing? Yes, I think we'll see you run through soon, right?
I will demonstrate a digital twin, yes, and it is possible to test or to get a trial license, I guess. But of course, to have it, to have a license for the digital twin, it is not for free.
Okay. All right. And
there exists some demo version.
It is, with a limited functionality.
Okay,
There
okay.
is
Just to get it to know and play around a bit with it. That's for free, right?
Yes.
Yeah, that's perfect.
But I guess
think.
what you demonstrate with this import of contract views
Yeah,
and
this
so maybe not for free.
No, this is
Well,
not-
that's powerful. we put some science in there, I think. And does this question from GH mean a document manuel utilisation? I think it's a manual if we have a user manual PDF in French for the SIPROTEC 7SS85. I'd search for it. In IMAL, right?
Can you repeat once again?
I think it's the question for a user manual in French. And I mean, we'll take that one in a written format, and if not, give it to our French colleagues, right?
I'm not 100% sure, but I'm 90% sure. I guess there should be French.
Okay, so we'll distribute a link to that document in the answers. We have now been live for 1.5 hours. We will stay live for you, but I think our eyes here in the studio and eventually your eyes out there in front of the displays need a short break. We'll be back in a bit less than 10 minutes. So enjoy a short break, give your eyes a bit of a rest and your ears. We'll take some fresh air, and let's meet again in, I'd say, 9 minutes. See you soon.
Gruppenbild.
All right, so welcome back after the break. I hope you had or enjoyed a short bio break. We did get in some fresh air. And now let's see, we've seen that Rainer finally managed to successfully export the project. And I think it was really helpful to see that just follow the red crosses and you are there where you need to change your project. And why this export was useful, that is something that Nina will now present to us and show us the digital twin and how the SIPROTEC 7 SS85 will look in there and what you can test in there. So let's go into the digital twin. Good luck.
Thank you, Michaela. So, yeah, in the next round about 60 minutes, I want to demonstrate you a little bit what we can do with our SIPROTEC digital twin and how to test the 7SS85. So these are, the mini agenda of the next 60 minutes. So I want to start with some stable conditions, injecting values with stable condition, and demonstrate you the disconnected image in the web browser view, and give you, of course, a general introduction about our digital twin. And then I will come to some fault scenarios. I want to start with an internal fault scenario, then come to an external fault with breaker failure protection, and then come to a fault in the bus coupler dead zone.
And it will be a very good repetition of the explanation of the different algorithms, of the 1 out of 1 algorithm, of the 2 out of 2 algorithm, and also how the circuit breaker failure protection will work.
Exactly. Okay, so Gert, can you please show my screen? Thank you. So this is the digital twin overview. But first things first, under project, you can here with this button plus sim, upload your sim file. So this is what Rainer exported, can be imported here with this button. I have already prepared this and upload the 7SS85. And here, this is also a nice feature of the digital twin. You can select the device firmware and the communication firmware with which the device is running. And this has the advantage that, for example, if there is a new version released and you want to retest something, compare the old version with the new version or something like that, then you can just simply change here the firmware version, and without any effort, you can test different firmware versions. Under test files, it is possible to upload COMTRADE files and XML files. So this is also helpful if you want to retest a fault scenario. You can just upload the COMTRADE file via this plus button here. Or, for example, if you want to test a sequence that you created with the Omicron state sequencer, you can upload it also here as XML file. And for our demonstration today, I also prepared some COMTRADE files for the different fault scenarios. So here you can see different files are already uploaded for some internal faults, for the couple of faults. And this is a nice feature to test some things here with COMTRADEs. And under routing matrix, under this tab, then you have to make the connections between the COMTRADE that you uploaded and the input of the device that you simulate. So for example, if I go here to the test scenario internal fault and go to the current view, so in this case, the source would be the uploaded COMTRADE file and the destination is the simulated device. And then you can set here via this matrix the connection between the COMTRADE and the device. And if your device is uploaded, your test files are uploaded and the connections are done, you're good to go and start the device by just selecting the device you want to simulate and use this stop button here on the top. And this is also what I already did in the break. So we have here now our simulated device running. And on this surface here, it is possible to directly inject current and voltages and to inject binary inputs. And you can, if you change here something, you can save these values that you entered here to simulate. You can save them. And here I also created some different scenarios. I will come to this later, what I prepared here. And with this button, you can inject the values that are displayed here. So with this first button, you can apply changes automatically. So as soon there is a change made and this button here is pushed, then these changes will be sent to the device. And can deactivate it again if you don't want to have this option. The other option here is to send to apply this value manually. So if you change something, then you have to press this button to send this value to the device. With this button, you can reset the values, and with this pause button, you can stop injecting values. And here under these options, then you have the possibilities to select the COM-grade files that you uploaded before, and to select the stable conditions or safe conditions that you saved earlier here from this direct injection. Okay, so I would say, Gerd, can you please give me the slides again? And I will demonstrate you what are the stable conditions I want to demonstrate. So the first one here is the scenario stable system, coupler closed. So here I am injecting 1 amp in bay 1 flowing towards busbar 2, also 1 amp in bay 2 flowing towards busbar 2, and then these two currents are flowing through the coupler and away from the busbar in bay 3 and 4, also 1 amp for each bay. So this is called later on stable system coupler closed. The second condition here is with the coupler open. So in this scenario, there's 1 amp flowing towards the busbar 2 in bay 1 and 1 amp flowing away from busbar 2 in bay 2. And same for bay 3 and 4. So 1 amp flowing towards the busbar 1 in bay 3 and 1 amp flowing away from busbar 1 in bay 4. And I also want to demonstrate a disconnector shunt. So here in this example in bay 1, both disconnectors are closed. And under these conditions, it is no longer possible to trip the two bus zones selectively. So here it is like one overall zone. And in this case, it is all colored in red because the preferred system here is the busbar 1. Okay, so much about the theory. Jumping back to the digital twin, please. Thank you. And now I want to show you real quick these two stable conditions I prepared. So let's start with the coupler closed scenario. So I just select here this pre-saved condition. And here, of course, also these binary values are set like displayed in the single line on the slide. So I sent this value to the device. And now I want to go to the online web browser. Okay, just redo the login again. And I want to show to you the single line diagram. So this is here, single line. And now you see exactly the colors as Rainer also has chosen before. So busbar 1 in red, busbar 2 in green. And the bays are assigned as shown on the slide before. So bay 1, bay 2 are connected to busbar 1. The coupler is closed. And bay 3 and bay 4 are connected to busbar 1 in red. And here on the bottom, you see the injected current values for all the CTs. On the right side, you see the differential and restraint current for the bus zones.
And you see also, unfortunately, well-known issue in the web browsers that at the moment the differential and the restraint current of the coupler zones are not available. It's available if you go to the online monitoring in Dixie 5, but due to a defect, it's at the moment not available in the web browser online monitoring. It will be fixed soon.
Exactly. And the check zone, last but not least, is visible. Okay, so let's change the condition. So I go from coupler closed to coupler open and apply these values. And then you can already see now the coupler disconnectors and the coupler circuit breaker are open. And now the current would be flowing like this. So towards the busbar 2 in bay 1 and away from busbar 2 in base 2. And the same for bay 3 and bay 4. So you can keep these two stable conditions a little bit in mind, because these conditions are always the pre-fault conditions in the test cases I demonstrate later. But last but not least, in the single line view, I also wanted to show you a disconnector shunt. So therefore I go to the binary inputs and for example, go to the bay 1 binary inputs. Here you can see at the moment the disconnector 1 is in position closed. The disconnector 2 is in the position open here. So I remove the open high signal and activate the checkbox for the closed high signal and send this to the device. And now you can see everything is red, because here in bay 1 we have this disconnector shunt. And as I told earlier, it is no longer possible to selective trip the bus zones. So here, of course, we only have the differential and restraint values for bus zone 1 and no longer for 2 separate bus zones. Okay, so I think we are good to go to test the first fault. And Gert, please give me the slides again. Keep the studio team busy here. Thank you. So this is what I want to demonstrate first. 3-pole internal fault on busbar 2 with a high fault current. So these are our pre-fault conditions, as explained earlier, with the coupler open. And then let's assume there's a fault on the busbar 2 between bay 1 and bay 2. And this leads to a current that is increasing and now flowing from both directions towards the fault. So I increase here the value from 1 amp to 5 amp and turn the direction of the second CT around. So both currents are flowing towards the busbar now. And for the busbar 1, everything is still stable. So we only want to simulate a fault on the busbar 2. Okay, thank you, Gert. So we start with the stable condition coupler open. And I want to replay the ComTrade internal fault.
1 of 1.
1 of 1. I think it will get clearer later why I named it 1 of 1. So I press this start button to replay this ComTrade. Okay, you already see here are some red LEDs glowing for the operate A, B, and C. So we have a 3-pole fault.
Maybe you read it's maybe too small, but the LEDs, the meaning of the LEDs, maybe you can read them.
It's the operate general from the bus differential and the operate phase A, B, and C.
Okay.
Okay, so as you can see, the disconnectors are now in intermediate position because the ComTrade file is finished. So to change it back from intermediate to stable conditions, I just go back to my prepared current values to fix this. Okay, everything fine again. So let's take a look at the fault that we tested. And therefore, I go to the web browser again. And this time, I go to the fault log in the web browser. So I open the fault log and take the one with the newest timestamp, so number 2 in this case, and scroll down because it is sorted from newest to oldest. So the newest one is the top one, the oldest one is the one on the bottom. So here we go, and we see there is a busbar fault on bus zone 2, and phase B and C were the first one that give this operate. And as we have a fault on the bus zone 2 and bay 1 and bay 2 are connected to bus zone 2, these are the 2 bays that are receiving a trip command. And this is what you see here. And of course, also, as we have a busbar trip, the inherent circuit breaker failure protection picks up. And these messages here are also worth to mention because they show the position of the disconnectors and the circuit breaker at the time of the trip. So this helps later on to analyze this fault and check, okay, which disconnectors were closed at the moment of the trip and which were open.
So typically when there's in the reality a busbar fault, so that means a whole bus zone has been tripped, all the management and the operational staff have to work to bring power to all consumers once again, and they will switching the disconnectors to ensure the power to all consumers. And when this is reached, then will start the analysis what really happened. Was it a wrong trip by the Busbar Protection? Mostly not. What really happened? And to make this investigation, it's very helpful to know really how was the disconnector image, which feeder was assigned to which bus zone at the moment of the trip to make the analysis. And really to log this information, we implemented to give the position at the tripping time and save it in the fault log.
Okay, let me do a quick step before I download the record because I don't clear my download folder so that you don't get confused. Okay, now let's have a look at the fault record. So I go to the web browser again and to the home button, and this time I jump to recording. So here, of course, I'm also interested in the fault number 2. It is possible to display this fault record directly in the web browser, but today I want to download it and open it directly in SIGRA, so offline. And therefore, I use this download option here. Takes some seconds. Okay. And then I go to this download folder, and here is our newly downloaded CFG file. Open it with double click. And now you see the currents in SIGRA. And the first question I want to clarify is why only phase B and phase C pick up at the beginning and not all 3 phases at the same time, for example. And therefore, I want to put all the phase currents in one diagram. This is possible by simply select the signal and drag and drop it to the first diagram in this case. And I do the same for the phase C current. So click on this and drag and drop. And of course, this is a little bit small now. So I increase the diagram height to 100 millimeters. Give SIGRA some time. It is a big record, of course, needs a little bit. And now I want to zoom in.
Looks very nice.
And I think now it is, yeah, almost at the first sight is getting clear why phase B and C are the first one to operate. Phase B is here the blue one, phase C is the green one. phase A was then the yellow one. And here you can see, if you compare phase B and phase C with phase A, you can see that those two phases have really a higher slope, a greater slope than the phase A. And this, of course, have an influence that on the trip time, I would say. Okay, then second step, I want to have a look at the differential and the restraint current. And the fault happened on bus zone 2. So I scroll down until bus zone 2 comes. Check. Okay, I think here we go. Yes, this looks good. And I will have a look at the values of phase B in this example. So I just want also to have the restraint and the differential current in one diagram. So I put this here and optimize a little bit and increase once again the height of the diagram.
Okay, zoom a little bit out once again, I would say.
Yes, as soon as SIPROTEC has finished.
Oh, still working.
Still working. Yes, now we're good to go.
Here, while Nina is zooming a little bit out, it's once again, I want to repeat what I have already stated in our last tutorial. In SIGRA, in every fault record, we see at one side the differential current. The differential current, that's a green one. And the restraint current is not the calculated restraint current. If you remember, I have explained we are working not with the calculated restraint current. The algorithm is every time working with the so-called modified stabilization current. The modified stabilization current is the same like the calculated stabilization current. As soon as the calculated stabilization current is higher or is increasing, as soon as the calculated stabilization current is decreasing, it's not going sinusoidal decreasing, it's decreasing a little bit in a linearized way. You see it here, this decreasing after the zero, after the black line, that's no sinusoidal decreasing. It's really this decreasing in this linearized modified way. Exactly, though when it's increasing again, yes, and here once again the calculated stabilizing current is higher than the modified, and then it's decreasing again. But still more, we are seeing here not the modified stabilization current, we are already seeing the modified stabilization current multiplied with the stabilization factor. Means if the differential current is above here this line in the fault record, we can directly state we are in the driving area. So as soon as the differential current is above the characteristics of the modified stabilization current multiplied with the stabilization factor, we can say, okay, we are in the driving area. Okay.
Mm-hmm.
And okay, so I will continue. And once again, if you remember, the 1 out of 1 algorithm, the 1 out of 1 algorithm has to be triggered by a jump of the stabilization current. And you see here, maybe once again, what are the numbers on the epsilon on the y-axis? It's I guess here that's 10.
This is 10, yes.
That's 10. So you see here really a very big jump. So we hear from the blue line under the black line, it's 1.5 milliseconds. So that means we have a jump of the stabilizing current within 1.5 milliseconds of nearly 10 times the nominal current. And this is even multiplied with the stabilization factor. So that means that's really a jump higher than 10 times the nominal current. And at the same moment, we are in the tripping area. That means from the very beginning, the differential current is above the restraint current multiplied with the stabilization factor. So that's really a clear indication this will for sure trigger a 1 out of 1 trip by the busbar protection. And from the fault inception, so that's here at the blue line, here that's around the fault inception. The black lines, that's 0, that's the tripping. Of course, the tripping of the algorithm without the delay of the binary inputs. So the algorithm has seen this tripping within 1.5 milliseconds in this case. Okay.
Okay, and this is happening with the 1 out of 1 algorithm, and this is why I called this test case internal trip 1 minus 1. Okay, enough about this fault. I need the slides again, please. Exactly. So we are now looking at a 1-pole internal fault on busbar 2 with a small fault current. So the starting conditions, the pre-fault conditions are exactly the same. We have these stable conditions, coupler open, and now what happens is a fault on busbar 2, same position. But in this case, I only want to simulate a small fault current. That means I don't increase the values, and I only want to simulate a 1-pole fault. And that means I just change the direction, as you can see here in bay 2, of phase A current in bay 2. So now there is a current flowing towards the fault in bay 1 and bay 2, but only with an amplitude of 1 amp and only for phase A. Okay, thank you, Gert. So I close this record and go back to the digital twin. Okay, as I said, I want to start with the pre-fault condition coupler open. So I inject these values and clear the LED so that we can check that everything is fine at the beginning of the fault. And now I select the comtrade file internal fault 2 minus 2 and replay this record. And here you may already see the difference. Now we only get here this operate signal LED for phase A. Okay, now it's finished. I jump back to the stable conditions. And we will have a look at the fault. So I go back to the web browser and home. And here I open the fault log in the first step again. Fault log, and now this is fault number 3. I scroll down to the bottom, delete here this download information. And now we can see here, once again, it was bus zone 2, and of course the check zone that trips, but only for phase A. Of course, the trip is nevertheless a 3-pole trip, but here this fault was only triggered by phase A. And of course, here once again, the trip signal is issued to in bay 1 and bay 2, because these are the 2 bays that are connected to bus zone 2. And of course, in this 2 bays, also the inherent circuit breaker failure protection will start simultaneously. So much about the messages. Now I want to open the record again. So I go to recording and fault recorder and download this time the fault number 3. Okay, everything is finished. I go to my download folder and open the record number 3.
Maybe now we can see a 2 out of 2 fault, huh?
If everything went right, yes, we should see a 2 out of 2 fault. I don't want to talk much about the phase current, just a small hint. Here you can see in the phase A current that the amplitude stays the same, but the phase changes. You can see this here. But now I go directly down to the differential and the restraint current, once again of bus zone 2. Scroll down a little bit. Bus zone 1, really a lot of signals for busbar protection here. Bus zone 2, and now of course we are looking at the phase A current because this is the one where the fault happens. So I put this in the same diagram, double click on the diagram to increase the height. And of course zoom in as soon as SIGRA is finished.
So now we can analyze the 2 out of 2 algorithm. And if you remember correct, the 2 out of 2 algorithm will be triggered for the first threshold exceeding when the 1 out of 1 algorithm can't apply. Means that we have no jump of the, oh, thanks, Red. Very nice. So that the jump of the stabilization current. So maybe let's start with the jump of the stabilization current. The stabilization current is a blue one, and I think it's very clear that we have absolutely no jump of stabilization current. So a 1 out of 1 algorithm is not possible, and we see here maybe here at the beginning of the fault. So here, not the beginning of the fault, when really the differential current starts. Okay, and when, and then the 2 out of 2 algorithm will be triggered when we have the first threshold exceeding. Maybe we can really here step by step. No, okay. Yeah, okay, it's fine. And here we have the first possibility, and here a little bit on the right side, to be a little bit more realistic. And now we will start the 2 out of 2 algorithm. And if you remember, the 2 out of 2 algorithm, 1 threshold exceeding is enough. But to be sure to start the second, to make a measurement window in the second half wave, we are starting and rest and break of the measurement of 8 milliseconds. And now I can't read it. So we have between the yellow and the blue line 8 milliseconds.
Yes.
The state time 8 milliseconds is for 50 hertz. Of course, we are testing here with a 50 hertz system. For 60 hertz, it would have been 6 milliseconds. And after the state time of 8 milliseconds, we will have a measurement window of 6 milliseconds. And within the 6 milliseconds, we need 4 threshold exceedings. So you can see at the very beginning, when the measurement window will be opened again, we will have no threshold exceedings. So it starts here, Nina, you can sign when, okay, here, beginning from this moment, we will have a threshold exceeding it again, and then we need 4. I think could be quite fine. So that really at the tripping times, there should be 4 threshold exceedings possible. So all in all, if you maybe once again with the blue cursor go at the beginning of the fault and set the time, now it's 18, or I can't read it.
16.5.
16 milliseconds. Really the tripping time of the 2 out of 2 algorithms, plus round about 4 milliseconds for type F binary outputs. So we have overall tripping time of the 2 out of 2 algorithm of 20, 21 milliseconds, depends on. Okay, now we had also a very fine repetition of the 1 out of 1 algorithm and the 2 out of 2 algorithm.
Okay, then slides, please. Thank you. So the third scenario I want to demonstrate is an external fault in bay 4. So we start once again with the stable conditions with the coupler open, and there's flowing current towards the busbar in base 3, over busbar 1 and away from the busbar 1 in bay 4. And now let's assume here is a fault, and the current, for example, increases, that is flowing towards the fault, and we receive a start signal for the circuit breaker failure protection, because, for example, a remote and differential protection system tried to trip this line and the breaker failed. Okay, thank you, Gert. So close this record and jump back to the digital twin. So stable condition coupler open are once again our pre-fault condition. So I check these values and clear the LEDs. And this time I don't want to demonstrate this by replaying a record, but directly changing the values that I apply here. So I was talking about a fault in bay 4, an external fault in bay 4. So I change here, go to this site for bay 4, and we say we increase the current that is flowing towards the fault. So I increase the number here from 1 to 3. And if you have these buttons here activated, he automatically chooses the same value for all 3 phases, and he will also balance the angles correctly. If you want to change one should change it individually, you can just deactivate this box, and then you can change each value separately. But in our case, we leave it like this. So I apply these values, and then we go to the binary signals. Of course, in a real case scenario, it wouldn't take that long, but I think we are okay for this test. And then I have to search the right binary input signal. These are a lot.
This will be the most challenging part for today.
So we are talking about bay 4, and luckily I practiced it. So here it is. We are in bay 4 in the circuit breaker, and this here is the circuit breaker failure start signal. So I activate this checkbox here and send these values to the device. And you see here now we get this 3-pole operator once again. I can deactivate it, send these values again, and let's have a look what happened. So I go to the web browser once again and open the fault log in the first step. So now it is fault number 4. I scroll down to the bottom, and now we see here the circuit breaker failure protection pickup, and 50 milliseconds later there comes the retrip of T1, and in parallel the T2 timer is started, and we see here this T2 time elapses, and we get the operate, in this case, from bus zone 1. Once again, in phase B and C first, but phase A will sure come later. And assigned to bus zone 1 is bus bay 3 and bay 4. And of course, these 2 bays are the one that will trip.
And just to remember, we have selected the breaker failure protection mode of unbalancing and not the IQA. And this will be interesting when we have a look in the fault record.
Exactly. And this is what we're doing right now. So I go to recording here and download the ComTrade file of fault number 4. Good. This time I want to start by looking at the binary signals. Okay, I don't know how good it is to see for you. Here, interesting is the circuit breaker start signal. So this was the binary signal that we activated. And here is the retrip T1 after.
After who?
I use this cursor here to the start of this signal, and of course the second one to measure a difference, and then you see this 50 milliseconds, and this is of course what we set here. And let's go to the trip T2. This should be 130 seconds, and I would be surprised if it would be something different. So now here we have these 130 seconds as the delay for T2. And yeah, really not much later comes the operate of the busbar protection. But let's have a look at the differential and the restraint currents. This time it happens in the trip happens.
Maybe once again, before we go to the differential current, do you have now the yellow cursor on the trip T2?
The yellow
yes,
cursor
okay,
is the
so
T2.
exactly fine, because the trip T2 now will stimulate the unbalancing of the bay current. And so let's see how the timing is.
Okay, bus zone 1 was the one that was relevant for this fault. So let me just scroll to the bus zone 1. And here, yeah, maybe we just look again at the bus of the phase B or C, because this was the fast ones. I select here phase B and put it in one diagram once again. And increase the height. And zoom in. Now maybe we need the operate time also as a reference. The operate of the busbar protection. So I put this cursor here on the operate of phase B, and the yellow cursor is on the trip T2 signal.
But I'm a little bit astonished in this example, because we have seen it a lot of times on a different way. I do not know, maybe the timing of the digital twin. It's a little bit surprising that the differential current already starts before the trip T2. I do not know the reason at the moment. Normally, the differential current should start immediately after the trip T2, but not before. But okay, this may be a reason also in the timing of the simulation. I do not know. Normally, this should not happen. Okay, but here with the trip T2, the unbalancing will start, and before it was external fault only, and via doing this unbalancing, we will how to simulate it to an internal fault, so that with the mechanism of the bus differential protection, we will trip the associated bus zones. And the restraint current is the magenta one, I would say. And once again, that's very important. With unbalancing, you will never have an 1 out of 1 trip. As with unbalancing, you will have no jump of the stabilization current, because the jump of the stabilization current will start typically maybe at the beginning when the circuit breaker failure protection picks up at all, but not in our case, the delay time T2 130 milliseconds later. So where Nina already have placed the yellow cursor is when, due to the unbalancing, we have the first time the threshold exceeding. That means the 2 out of 2 algorithm will be triggered. So that's at the yellow point. And then once again, 8 millisecond dead time. So the 2 out of 2 algorithm. So here, here we will start once again a measurement window of 6 milliseconds. So for at least around about 1 millisecond, we will have no threshold exceeding, but immediately after, we will have the threshold exceedings, and at the yellow point, that's the tripping.
That's 6 milliseconds
that's
later.
6 millisecond, and okay, that's fine. So we see it's absolutely fine to have for threshold exceeding, and the trip, okay, it's a little bit later. We see here because we don't know how it is synchronized our protection cycle really with the measurements, and here is a tripping around about half millisecond later than when the measurement window ends.
6.3 it is.
Yes, okay. So here, really, at this point, we will trip the associated bus zones after the unbalancing of the bay current. Okay, fine.
Okay, then let's have a look at the bus coupler faults. So here I have 2 fault scenarios. To speed it up a little bit, I want to explain for both cases the theory at first and then do the testing. So the first fault case would be a fault in the dead zone of the bus coupler in a 3-pole fault. So the pre-fault conditions would be that current is flowing towards the busbar 2 in bay 1 and bay 2, flowing through the coupler and flowing away from the busbar 1 in bay 3 and in bay 4. And now let's assume there is a fault here on this position, so between the 2 CTs in the coupler. And this means here is the fault, so the current is flowing towards the fault. So now the direction in bay 3 and 4 and in the right coupler CT changes. And now from both directions, the current is flowing again towards the fault here. And this is happening 3-pole. The second coupler fault I want to demonstrate is almost the same, but 1-pole. So here, completely same pre-fault conditions. And now the direction of the current in bay 3 and 4 are changing and in the right coupler CT. And now current is flowing towards the fault from both busbars, but in this case, only one phase. So only for phase A. Okay, thank you, Gert. So close this record and go to the digital twin. Clear these LEDs, and we say we want to start with the coupler closed condition. So I select this one and apply these values. Maybe we can also have a quick look on the display. So here you can see this pre-fault condition, the coupler is closed. And now I select at first the coupler 3-pole fault and replay it. Okay, you see the coupler CT has opened. We have an operate, a 3-pole operate, of course. And now it is finished. And I change back to the stable conditions coupler closed. And I think this time it is sufficient to only look in the fault record, in the fault log real quick. And therefore I go back to the web browser again and open the fault logs. Now we have 5 entries. The number 5 is the newest one. I scroll down to the bottom. And now you see here, there's the operate from the coupler zone. And since we have these 2 thresholds in the bus coupler differential, the first one was for 3-pole faults and it was set to 1 amp. This means as soon as we have a differential current above this threshold and for 3 phases, then we will immediately trip both bus zones in overlapping mode. And the second threshold was set to 5 amps, and this was the threshold for the 1-pole faults. And that means as soon as we have to exceed these 5 amps, then we will also get to overlapping mode for 1-pole faults. But in in between. So for currents smaller than 5 amps.
And to win 1 pole fault.
And 1 pole fault, of course. There will be a selective tripping with the end-fault protection involved. But first test scenario was 3-pole fault. So, and this is why we see here this operate for both bus zones. And let's demonstrate the second scenario. The coupler closed scenario is already active. And now I jump to the coupler fault 1 pole and replay this one. Maybe I clear the LEDs.
And now we're expecting really a so-called sequential tripping, or first only tripping the coupler, applying the end fault, and then only the faulty zone should be cleared.
Exactly. Okay, now it is finished. Go back to stable conditions. And you already see here, it is only the LED for phase A active. And let's have a look at the fault log. It's number 6 in this case. And here you see only bus zone 1 trips finally.
Can we see the trip of the circuit breaker first? In the log, the trip open command, coupler, circuit breaker, circuit.
You mean this one?
Is this a coupler? Yeah, exactly. Yeah. Yes, it's here 384. And when since the bus zone 1 tripped?
Here.
458. Okay. Fine.
Okay. So these are the fault scenarios I want to demonstrate. Maybe just some small hints about the digital twin. Today I demonstrated the centralized setup, or we demonstrated the centralized setup. It is also possible to simulate a distributed digital twin with up to 20 devices if you have the digital twin L license. Okay, then I would say we are finished with our second block and have time now for your questions. Great. And then there will be another break.
Perfect. You can stay there.
Oh, okay.
You don't have to leave the stage. I think it's fine for us 3. And there are questions. I think we still have some of the first round and continue to try to answer them chronologically, if that's fine for you. So the first one is interesting. Can one get the TX file? So will you share that?
Sure. Yes,
okay.
I would say so.
So yes. Just get in direct contact. I think we will not be able to put it as an attachment, but it will be fine as a direct mail. And then it's a question of which circuit breaker is connected to which bus bar. Oh, I think somewhere in the model it's circuit breaker 2. So the question was from GK. And why the circuit breaker 2 is connected to busbar 1 and circuit breaker 1 connected to busbar 2, but I guess it was vice versa, right?
Not circuit breaker, disconnector. QB is a
that's true.
QA is typically the circuit breaker. But I guess we have already answered this. It doesn't matter. It is only for the demonstration, and in reality, it should apply to the substation.
How it's
should be marked as
that's I think it was a similar one.
Yeah.
And then the question from NHS is just a configuration about bus coupler differential, and I think we've seen that how to configure, right?
Small hints we gave also today and in the last tutorial.
Yeah, so in tutorial 2, more information about the bus coupler differential protection. And then the next one, how many different, coming from FJ, how many different CT ratios possible at sitting? At sitting or for the settings? Might be a typo, and I think CT dimensioning will follow in our next part of this session, right?
Yes, you're right, but I think this answer will not directly be answered, but it's a CT ratio, how many there's no maximum number.
Okay.
So in principle, you can give a different CT ratio to each CT you're configuring.
Perfect. Thank you. And then the next question came in from IK. Is it possible to change significant feature after I got the shortcode of the relay? Let's say if a busbar protection had been ordered and there's a change in the single line diagram from the client.
Yes, this is possible. You can order a so-called DAF file via the SIPROTEC 5 configurator, and there you just have to enter your serial number of your device, select the significant feature you want to have in the future, and proceed with the order process.
Okay, so it's possible to change that. Great to know. And then HM wants to know, where does the CT star points face for busbar protection?
There's not both is possible. The CT star point could be based both be in direction of the busbar or in direction of the line, but you have to configure it in your single line diagram. When I remember in our configuration, we every time configured it as towards line. I think that's a default configuration. But you can select the current transformer in the single line, and then there, with the right mouse click, there is, I guess, invert the direction of the CT star point, and then you can change it to the direction of the busbar.
Okay, thanks. The next one is a bit more tricky. I think at least it's a longer question that came in from VB. Could you please explain a little bit more about CT connection, so grounded towards busbar or line? Because VB is a bit confused, and then it's a lot of information from the manual, and I'm not sure if it's helpful if I read all of this to you, or if we just take this in general. So explain a bit more about the CT connection, and then you might give a detailed answer in a written format.
Yes, I think when I have already started, that's indeed a little bit complicated. It's also written in the manual, but I agree it's maybe a little bit complicated to make maybe a summarize. How to change the direction of the CT star point, I have already explained. It will be a little bit more complicated if we are going to the IEC 650 compliant solution, where you might have an independent protection device as a merging unit with a different definition of the direction of the star point. And this also was not very clear at the beginning, defined in IEC 61850. So we decided, as every time when something is not completely clear, so we decided to make it as a setting to also to be compliant to third-party merging unit and so on. The major thing is this neutral point in direction of the reference object should be both in the merging unit and in the central unit set either to no or to yes. But I think it's worth here to give a written answers. I would prefer.
Perfect. Thanks a lot. And the next one is a rather short question. Let's see how long the answer will be. So SB wants to know, how do you handle mismatch of the CT polarity in the single line diagram?
Mismatch of CT polarity.
So if one is looking in the one direction and the other one in the other, maybe?
Mismatch, okay. The CT polarity, I guess the CT polarity is the direction of the star point. What means mismatch? It could be in this direction or the other direction. More or less, it leads to an multiplication of the current with -1. So I do not know what is the reference. Let's state direction of the line is +1, and direction towards Busbar is all the currents will be multiplied with -1. And that's the background here, because in reality this leads to a change of the polarity of the current, which will be measured by the device, and you have to give this knowledge to the device via the symbol in the single line editor, and whether it's towards Busbar or towards line will be at the end handled. One will be multiplied with -1.
Okay. Then we have a question in German bezüglich dezentraler Sammelschienenschutz. So I tried to put this in English, but I'm not sure if I have all the necessary vocabulary for that. So we talk about decentralized busbar protection without own CTs, so current transformers. So, and then the question is there a symbol for the Einschub? And that's where I struggle. Maybe my experts here have an idea, but I think we'll take that question offline. And then
maybe my German is not good enough to really understand what is meant by Einschub.
No. So maybe we take that offline and go on a one-on-one discussion, and then both of you can talk in German to each other. That's eventually even easier. Then let's see. CT, but I guess that's not a current transformer, but that's a name, wants to know, is it possible to see all IEC 61850 settings corresponding of your configuration?
In our example, we didn't do any IEC 61850 settings because we had this centralized approach where all the currents are directly connected to the 7SS85. And yes, I inserted this BB module, or we had this BB module available, but we didn't make any settings for this.
Okay.
This case.
So we cannot show it. It's possible to have them, but we cannot show them.
We can show the IEC 61850 settings when we will demonstrate our distributed busbar protections, and we will have IEC 61850 settings available.
There's more to
next
see
webinar,
next
right?
Of course.
So, as we already told you, stay tuned. Watch out for our next webinar on the 4th of April. But now, stay tuned right to this one, because we continue the round of questions and answers, and we still have a third part planned for you for today. And then TDM wants to know, eventually it's even already done, could you better explain the functionality of coupler zone and its settings?
I think it's also recommend to watch our second webinar.
The second webinar. I was just thinking about, I think this coupler zone was mentioned a few times in the second tutorial, so it's worth to take a look at that again. And if you still have questions, then just contact the experts.
Of course.
Yes, you are there. And OK wants to know, can we use normal auxiliary contacts for SIPROTEC busbar protection?
I think the question is what really are normal auxiliary contacts. I would say yes, but as normal auxiliary contacts, we recommend normally to use the so-called limit switches, when really we have the closed or high command really at the moment when the auxiliary contact, or when the primary switch is at the end position. That is called limit switches. And if this is normal auxiliary contacts, I would say yes. There sometimes maybe also overlapping auxiliary contacts is expressed as normal auxiliary contacts, but they can also be used.
Okay, thank you. And then the question from AK. Does the SIPROTEC 7SS85 have RSTP protocol instead of PRP?
RSTP protocol is possible, but we can't say that the 7SS85 uses RSTP instead of PRB. RSTP is an available protocol. 7SS85 is a fully compliant modular devices with all functionality of SIPROTEC 5, and you can select RSTP. But RSTP, once again, outlook for our next webinar is not a possible communication layout to have redundancy of the busbar protection. Here only PRB is possible. Or for the answer, have 7SS85 RSTP protocol instead of PRB, I would simply say in the first step, no.
Okay.
No. Of course, HSR, but all these communication layouts will be really explained in detail in our next webinar. But all is possible: PRB, star communication, HSR. Where is the Grandmaster clock be located? Grandmaster clock with GPS, without GPS, and I think we have a separate webinar for this. And it's really a lot of stuff. It can't be answered here now.
Yeah.
And here also at one, we will explain a very application for the RSTP protocol when we have to extend the switch when we don't have enough ports in the first switch, and then we will extend for the second switch, which is necessary via RSTP protocol. Yes.
Perfect. So thanks again for all your questions. We continue to answer them. And we continue the webinar. I think the next one I see here is, would it be possible for a better learning effect to also receive the ComTrade files, the fault records? I assume that all of those questions come from the same person. And Nina already mentioned, yes, you can get access to that. I think it's possible to send that via mail or via Sycofax for download.
Share this.
There are still some questions. We keep those for the next question and answers round because we still have some time planned for you. Now it's almost 3 hours that you are listening into us, and thanks for still staying with us, and stay tuned. Enjoy a short break, have a coffee or a tea, a sip of clean air, and I think we'll meet again a bit after the full hour. So see you in a few minutes. So welcome back again after the second short break. And I think it's time for part 3 right now of this Busbar tutorial number 3. And soon Rainer will tell you about, or will tell his knowledge on CT dimensioning. And before that, I like to mention that if that was a bit too fast for you, what you've seen in the digital twin, in the configuration, and with this product or project configuration in Dixie, you have 2 possibilities. Just watch the same stuff once again in the recording of fast, or do a practical training in the Power Academy. So you can just book your training there and then go into an even more deeper dive with this, with hands-on, with tutored hands-on, and a training there. But enough advertisement for the Power Training Academy. I think, Rainer, let's go into the CT dimensioning. Please share your knowledge on that with us.
Okay. First part for today's webinar. Get to know more about CT dimensioning. CT dimensioning may be sometimes a little bit complicated stuff. I want to give you now for today the basic knowledge. Let's start. Okay, CT layout parameters. In general, we could really state that the CT requirements for the 7SS85, there have been the same CT requirements for the old 7SS52 systems, and the CT requirements are very low. In the first step, they are quite low in comparison to the high impedance busbar protection. So in the 7SS85, we need no dedicated, no special CT types. Whereas for the high impedance busbar protection, really only the class PX, according IEC 644-1, is required. For low impedance busbar protection, we stated and still stated, but in the meantime, we are a little bit more, how to say, careful than in the past. We can use different CT types. We can use different CT types, but new is we say don't avoid a mix of different CT types within one scheme. And especially to avoid the mix of class B and the TBZ class, because there is a quite different behavior regarding the DC component and so on. And this might, for sensitive application, may cause problems. Whereas different CT ratios, and if you remember, this was one of the questions. This is no problem at all. That's low impedance busbar protection. We are using a numerical way, and the CT ratios could be matched without any problem. And as already said, in principle, there are as much difficult ratios possible as you have different CTs. That means in case of a large distributed busbar protection with up to 48 CTs, theoretically you can have a different CT ratio for each of this CT, whereas in reality this would be not the case, I guess, because so many different ratios are not available. Absolutely no problem is that the CT core can be shared without any problem with different protective devices. You can use the same CT core for our busbar protection, use the same CT core also for the overcurrent protection or anything else. Whereas in the high impedance busbar protection, really a separate CT core explicitly for the high impedance busbar protection application is required. But the CT requirements are also very low in comparison to the other protection devices. So the KDD, I will later explain how we come to the KDD. The KDD, the transient dimensioning factor, is for the 7SS85 0.5. It was the same for the 7SS52. For transformer differential protection, line differential protection, we need a KDD of 1.2 up to 5. And especially for distance protection, we need a very high KDD. What is for sure, if somebody says, okay, the CT has been dimensioned to fulfill the requirements for distance protection, to fulfill the requirements for transformer protection, then no further calculation is necessary. You can immediately say, okay, it's fine for distance protection. No questions. We can use this core also for the Busbar protection device. This sometimes astonish a little bit how do Busbar protection. It's so important, it's so dangerous to risk no wrong tripping. The CT requirements must be very high for such an important protection like the Busbar protection, but the difference is the case. Very important to state that the 7SS85 is stable, and this is proved also via a KEMA certificate for remanence for up to 80%. The calculation I will do is assuming that the remanence will be below 80% remanence. If the remanence will be higher, we will introduce soon in our manual how to say corrections and to make the CT core the requirement a little bit higher, also to deal with a remanence of more than 80%. But for today, I will assume a remanence of up to 80% only. Okay, this is also a quite often asked questions, and we have no numerical limit. What is between the highest and the lowest, the maximum and the minimum CT ratio? But even the weakest CT must fulfill the requirements. That is important. So that really all used different CTs must fulfill CT requirements. The CT requirements I will explain in the next slides. Let's explain a little bit the necessary data to make such a CT dimensioning. That's according IEC 644. The system data, the ISSC max, sets the maximum short circuit current in the substation you want to protect. So typically, this maximum short circuit current will be given by the infeed, by how much power can be supplied to the substation. The CT data, IPN, that's the rated primary current. If you remember, that was 1,000 amps for the feeder CTs and the 2,000 amps for the CTs and the coupler. We need SN, that is the rated CT power. We need RB, these are the rated resistive burden. Very important, that's the KSSC, that's a rated symmetrical short circuit current factor. And we need the secondary winding resistive, means the resistance of the secondary winding of the primary CT, and with the abbreviation is RCT. And R-P, that's the connected burden. And the connected burden, of course, depends on the resistance of the leads, R leads, plus the resistance of the relay. This is more or less fixed. The resistance of the relay of the 7SS85 is 0.1 ohm. Some notes. If you have CTs according to ANSI, IEEE, or the British standard, this data should be converted to IEC data. A lot of problems I have quite often with the RCD, the secondary winding resistance of the primary CT. Often I will be asked, okay, CT dimensioning, and I say, okay, it's fine. I can make for you a rough calculation whether it's fine or not. And then often the secondary winding resistance of the CT is not known. And if you use the program CT-TIM and you don't enter the RCD, they will work with a 20% of the rated power will be done. But this can lead really to an over-dimensioning of the CT. So I really propose and give the recommendation really to measure. It's quite easy to measure the RCT, to measure the secondary winding resistance of the primary CT. In case if you use a primary CT with a secondary nominal current of 5 amps, attention should be paid to the resistance of the leads, because then here the resistance may be quite high. The resistance of the lead, of course, is every time an issue really in a distributed busbar protection or in a wide area busbar protection, when a centralized busbar protection may be used, and here's the resistance of the lead may be quite high, which could once again lead to an earlier saturation of the CTs. And that's the reason why in a wide area substation, you should, or it's preferred to use really a distributed busbar protection. We will see it later in the equations for the CT dimensioning. Why is the KTD 0.5 for the 7SS85? First of all, it's very important to understand when really the stabilization factor is important when we have NCT required and when we have a CT saturation. If you remember this slide where we explained the behavior of a CT saturation after around about 3 milliseconds or anything more. You remember with the 1 out of 1 algorithm, which will be blocked when at the very beginning we have a strong peak, a strong increase of the stabilization current, but we are not in the tripping area, and that's the 1 out of 1 algorithm will be blocked, and then only the 2 out of 2 algorithm will be worked. And it's important to stay that in this phase with a high DC offset, the K factor, whether the K factor is 0.5 or whether the K factor is 0.8, which is the maximum, has no importance. The proper dimension K factor is important in the static state here on the right side here of our simulated fault, when really the DC offset has been declined and has gone back to 0. Because why is this DC offset? Okay, this DC offset may cause an earlier CT saturation, but on the other side, it will deliver us a very high stabilizing current. And via our mechanism of this modified stabilizing current, we have so much no problem really to overstand and not to wrongly trip at the beginning of a fault. Really, whether the CT dimensioning is not correct, you will see in the static state, means when the DC component has been declined. So the wrong tripping of an external fault. Why? Because the CD is not dimensioned correctly will typically apply not in the first period. It will apply when the fault will not be cleared fast enough after roundabout, depending on the net constant, after about 150 milliseconds. It will apply here exactly. And here, it's now in the simulation, we say that's the saturation time, the time of saturation. And to make a roughly calculation, we can say the limit of the stability is really given when the differential current is the same like the stabilization factor multiplied with the modified stabilization current, according to our tripping characteristic. Let's assume, because we need an safety margin also, let's work with a stabilization factor of 0.5. So we get at the time of the saturation that the maximum differential current is the same, you will see here, like the short circuit current. Or in other words, the stabilization factor K multiplied with the maximum stabilization current. So that's 0.5. That's our stabilization factor here in our case. And 2 times the short circuit current. And so here really the differential current is the short circuit current. And if you look now here once again to the diagram, and this leads directly to the states that the KTT is 0.5, and 0.5 means that the CD must be able to transmit the half of the short circuit current, because at the half, at omega multiplied with the saturation time, 90 degrees for 50 Hertz systems, this means 5 milliseconds. At 5 milliseconds, we have transmitted the half of the short circuit current. And that's the same like the statement, the KTT is 0.5. And that we don't need more belongs to our algorithm, belongs to our modified stabilization current. Let's a little bit think about this stabilizing factor K. As already said, only in the steady state, when the DC component has been declined, the K factor has really an influence to the stability. And that directly leads to the statement I have shown. A wrong tripping in an external fault due to wrong CT dimensioning will occur mostly in the steady state, means will happen 100 milliseconds after fault injection. With the saturation free time of omega multiplied with dsat more than 90 degrees, means the saturation free time is more than 5 milliseconds in a 50 Hertz system. Oops. Thanks. We can remain with the default setting of 0.65. As we learned, with a stabilization factor of 0.5, we are exactly at the limit. And we don't want to be with the stability at the limit with the busbar protection. So we all every time have to calculate a little bit a safety margin also. If the saturation free time is less than 90 degrees, means the saturation free time is less than 5 milliseconds for 50 Hertz systems, then we should simulate this with the program, the CT-TIM program, really to determine the required K factor. Here really a detailed calculation is quite complicated. To give you a rough impression how the K factor in dependency of the saturation free times looks like, you have a look to this characteristics on the right side. Here we have the saturation free time for 50 Hertz systems. And you will see when the K factor will be 0.5 every time when there is a higher saturation-free time than 5 milliseconds. And the minimum saturation-free time, and so that's round about 2 milliseconds, then we should use a K factor of 0.8. But whereas that's pure calculation without safety margin. So in reality, I have said for saturation-free time of 5 milliseconds, we should use the stabilization factor of 0.65. And even with the higher stabilization factor of 0.8 should be used in the maximum, you see it here in this table, for saturation-free time of around about 2 milliseconds and 2.15 milliseconds around about. Okay. Let's a little bit calculate. And let's talk a little bit about abbreviations. That's every time not so easy, and in different literature and in different manuals, there are different abbreviations used for the more or less same terms. The required symmetrical short circuit factor, that's the KDT 0.5 for the 7SS85. Multiplied with the maximum short circuit current of the substation divided by the primary rated current. So all these considerations must be done for each CT, for each different CT type with maybe different ratios. If they are used every time the same CT with the same CT ratio, of course, you can do this calculation only once. We need the effective symmetrical short circuit factor, or in our manual now also used as the operational ALF. That's ALF, I do not know, that's a limiting factor, the accuracy limiting factor, it's called. And this, but I will name it more the effective symmetrical short circuit factor. That's the rated symmetrical short circuit factor multiplied with the rated burden plus the primary resistance of the CT divided with the connected burden plus the primary resistance of the CT. And the CT is fine if the effective symmetrical short circuit factor is higher than the required. And in addition, due to the limit of the measuring range, you have to see whether the maximum short circuit factor divided by the primary rated current is smaller than 100. Okay. A small example. We have a busbar protection. We have a transformer with a primary current of 600 and the secondary rated current is 1 amp. We have a 5P10 CT type with a rated power of 15 VA. The resistance of the secondary winding is 4 ohms. We have leads, they are 50 meters, and we have copper. The leads are copper with a cross-sectional area of 4 square millimeters. And as already said, the burden of the relay, the burden of the 7SS85 is 0.1 ohm. The maximum short circuit current is 30 kiloamps. We start with the required symmetrical short circuit factor. That's the KTT of the device multiplied with the maximum short circuit current divided by the primary rated current. That's 0.5 multiplied with 30 kiloamps divided with 600 amps. So the required symmetrical short circuit factor is 25.
let's come to the operational symmetrical short circuit factor. Here we need some additional calculations. The resistance of the leads, that's 2 times the specific resistance multiplied with length divided with the cross-sectional area. That's 2 times 0.0179 multiplied with the 50 meters divided by the 4 square millimeters, and you will see also with the dimension everything is fine, so the outcome is 0.45 ohms. The rated burden, that's the rated power of the CT divided with the secondary rated current squared, so that's this 15 VA divided with 1 amps squared, so the RP is 15 ohms. So the effective symmetrical short circuit factor, or the operational ALF, is the rated symmetrical short circuit factor multiplied with the rated burden plus the resistance of the CT divided to the connected burden with the plus the resistance of CT. So that's 10. So that's this rated. This after this 5p10. That's a rated symmetrical short circuit factor, and 15 plus 4 divided with 0.55. The 0.5 are the 0.45 plus the 0.1 of the relay of the burden. So that's this 0.55 plus 4. So the effective symmetrical short circuit factor is 42. And so the effective symmetrical short circuit factor is higher than the required, so it's fine. And we have to check also the limit of the operational. So that's 30 KE divided with 600, that's 50, and that's smaller than 100. And so in this case, everything is fine. CCD is correctly dimensioned. If not, if according to this calculation, it comes to a problem, as already mentioned, we should start and dimensioning with the program CT-TIM and to find out whether it will be still possible to fix this, that the CT will not fulfill this equation, to fix it with a higher K factor. And that's here's this CT dimensioning with the program CT-TIM, which is maintained by our colleagues from the PTI. So I am finished.
I'd say almost finished. We still have some questions, and we will take some time to answer them. And let's see, find some space for me right here. And you will see those questions enlarged a bit, and I will scroll down to kind of, we continue the journey with the older questions and try to answer as many as possible in the next minutes. I think we have a little bit less than 15 minutes. There you go. CT had the question, so I think we can skip the ones from Vivi. We already had some answers to those. And CT wants to know, what are the differences comparing with other simulation tools, such as Omicron, for instance?
Okay.
I think that refers to the digital twin.
Yes, I guess. Yes. So the digital twin is the simulation of our protection device, our SIPROTEC protection device. And Omicron is, of course, a testing tool for protection device. So there's, of course, a difference. And Omicron does not offer a digital twin version yet. So
if Omicron offered a digital twin, we could connect our SIPROTEC digital twin and really simulate values in there, but we don't need to because we have it all in one box, right?
Yes,
yeah.
you could say it like this. Yes.
Okay, perfect. So thanks for the question. And then CT wants to know, in case of a centralized protection, how do you ensure the backup?
What kind of backup? I'm not sure. Backup of the project, backup protection.
I'd understand
I
it
guess
if
it
it's just the protection function. So if
Yeah.
I talk about just one device doing all the central protection functions, what's happening if this device fails?
Yeah, okay. First of all, you can already add some backup protection function to each bay, means to each feeder, to the coupler. We have already added circuit breaker failure protection as a backup. You can also add overcurrent protection to each feeder bay. You can add up to 10 directional overcurrent protection, even in the centralized busbar protection. And you can also add backup protection, maybe some kind of frequency protection or overvoltage, undervoltage protection. That's all possible.
Okay.
But in general, you will have anyway in a substation, not only busbar protection, you will have anyway. So every protection is not allowed to have no backup.
Yeah.
So that's the backup functionality we have available directly in our centralized busbar protection. But I think in any case, you will have anyway an independent line protection device in any case.
Okay. Thank you. So let's take the question from VB. So assume a fault in the dead zone of the bus coupler. If VB got it correctly, the BBP will trip both bus zones in case of a 3-pole fault and only one bus zone in case of a 1-pole fault. Is this correct? Or is this understood correctly?
Yes, I think I know what is meant.
Perfect.
So in case we have these setting values that we took a look at earlier. So there are these two thresholds for a 3-pole and a 1-pole fault. And as soon as we are above this threshold, the device will trip in overlapping mode. This means it will trip both bus zones. In the settings we chose, we had it for the 3-pole faults to 1 amp and for the single-pole faults to 5 amp. So as soon as we are above this 1 amp and we have a 3-pole fault, yes, we will trip both bus zones immediately. And if we only have a 1-pole fault, then the tripping will be sequential. That means in the first step, the coupler CT will open, and then the end fault protection gets active, and only the selective zone that is feeding the fault will be tripped. And for a more complete or comprehensive answer, I would once again recommend our second tutorial.
Yes, around end fault protection, right?
Maybe one additional hint why we selected exactly to trip the 3-pole faults in an overlapping mode and the 1-pole faults non-overlapping in the sequential way. The reason behind, of course, is that the sequential tripping took quite a long time really to finally clear the fault. And when we implemented this function, I did this together with a customer in Tasmania. It was Transnet, and they requested more or less this functionality from our device, and they did some very interesting investigation in their network, and they came out. It's a little bit simplified. In reality, it depends also on which kind of power you have. If you have more wind power, it's more sensitive. If you have more inertial, conventional power, it's not so. But at the end, it came out for high current 3-pole faults. It's maybe quite critical to wait long because an islanding of the network could happen. So it's maybe a good idea. High current 3-pole faults, really, it's better to clear it very fast but not selective. Whereas for single pole faults, this islanding is not so sensitive, and you may have more time really, and the selectivity is more important and can be accepted for one pole faults. And that's the reason why we make this example to make the three-pole fault clearing in overlapping and the one-pole fault in the sequential way. But if you are interested, I have already said there exists a very good paper which I have written together with the guys from Transnet. And if you are interested and you will send me an email or anything else, I will forward this paper to you.
Thanks. Yeah, interesting stuff. Yeah, knowledge from the customer and from the customer's network is worth a lot. That's true. And next question came in from RPS, and RPS wants to know which settings are to be preferred to avoid the propagation of one bay fault to another one. Did we see this setting?
I don't understand what this means. Do you understand the question?
Like cascading eventually, but okay, too complicated.
To avoid propagation of one bay fault to other one. No, sorry. No
okay, so we'll take that offline, and eventually it gets clearer if we find more there, and if not, this can also be done on a 101 discussion. And taking care a bit of the time, let's jump to the next one. I think we've talked about CT polarity and to be changed by the star point for all the bays. But let's jump to the next one from HNS, where the impacts on this. Does this continue? There we go. Whether the measurement ID number in function group connections is to sequential and it can be modified. Any impacts on this? This is also a fragmented question.
Measurement ID. You know,
maybe something again for the
maybe an internal number of our measuring point. I'm not clear with these questions.
Okay, let's see if we can handle one last question from RPS. What difficulties will be faced when using two different make relays? I think it might be relays from different vendors. For example, in one bus section and another in the incoming or outgoing bay. So what difficulties can be faced if we talk about relays from different vendors? I think, or different make relay, different types of.
Maybe we are already tired.
Yes, I'm not sure. And it's tricky to get the meaning of the question. So let's see if we can.
Also
not sure if this is fine.
Relays to make the binary outputs.
Maybe if you get the questions in the next days and you will do them, that brings me to how we continue, right?
I am even not sure whether it's really different relays from different vendors or different types of binary outputs.
Maybe something like this. So we'll take this question to you in a written format. You will get a written answer. And since we are already almost running out of time, it's fine that we quit answering right now the questions here. Nevertheless, all the questions that are still in the questions field will be answered written. And you will receive a mail with that. And you will receive a mail with access to the recording. I think you already found out that we have the recordings of the former 2 tutorials around busbar protection, and we referred to them quite a few times today. So if you haven't been part of those, take the chance and watch the recordings of the tutorials 2 and 1. I hope that you will make extensive usage of your knowledge around the application of the centralized SIPROTEC 7SS85. you've learned today and around the CT dimensioning. If you want to train what you've learned here, I already mentioned our Power Academy, and I think the link to the Power Academy will also be part of the one of the packages you will receive from us. And to continue this journey and this webinar series, it's just now, well, I hope that I will see you again, or we hope that we will see you again around the 4th of April for our last tutorial in the session of Busbar tutorials. And there we will do a deeper dive on the application of the distributed SIPROTEC 5 Busbar protection and on maintenance functions. So for today, I hope that you and your grids will stay safe and protected. And we here from the studio say goodbye for today and see you in the next tutorial. Take care.
Goodbye.
Bye.